and welcome to another 5-minute video for the level 3. In this session we're going to be talking about the electrical double layer. This is all about forces of repulsion. So what is the electrical double layer? It's all about repulsive forces, and it's all about the surface charge on particles when they're in solution. And we're going to be looking at the first layer of charge around a particle known as the Stern layer, and then we'll look at the layer beyond that, which is known as the Gouy-Chapman layer. So here we have a particle. We may not realise it, but in solution most particles have a charge on their surface. It could be positive, it could be negative. In this one I've just happened to have randomly chosen negative. So if you imagine now that you've got a solution full of positive and negative ions, if this particle is full of negative charges on its surface, then it's not difficult to imagine that it may attract positive ions that are within the solution. It does so, and it forms this layer of positive ions. And this was first identified by Stern, and therefore this is known as the Stern layer. Now that you've got this sphere of solute with all these positive ions there, you might imagine that it will now attract some negative ions out of the solution to form another layer. And that's what it does. But you know, this surface is a bit more dissipated than this, and so you get some negative ions but some positives. And then there'll be another layer beyond that and another layer beyond that, where the ratio of positives and negatives keep changing until eventually you've got 50-50 and you're back into the bulk of the solution. But if we look very closely at this, these ions carry with them the solute particles, because they're the water particles. So they're holding on to a certain amount of water that's surrounding this particle. And it's a bit like looking at some frog spawn, where the black bit in the middle there is your particle with the negative charge on its surface, and this gel all around it is it's the water that's being held there by those ions. So if you imagine a particle travelling through a beaker of water, that individual particle isn't travelling on its own, it's captured a sphere of water all around it, and that's moving with the particle. So you see where the repulsion comes in now. If you've got two of these things, then the particles can't get together because that sphere of water is in the way. It's like a barrier. Just like with the frog spawn, the two black nuclei can't get together because this sphere of gel is in the way, stopping them coming together, keeping them apart. So there is a point at which the water will be held close to the particle, and beyond that the water is not held. And that there is known as the Gouy-Chapman layer. And this shear plane is where zeta potential is measured to. So this has a very negative charge, maybe minus 30 milliamps, and you've got positives and the negatives. As you move away until you get out into the bulk of the solution, that will be 0 milliamps where you've no charge. The point at which this shear plane breaks away and the sphere stops travelling, then this is what we call the zeta potential. So the larger the zeta potential, the thicker that layer is, and the harder it is for particles to get together. The smaller the zeta potential, the thinner this layer is, the more likely you are that particles will be able to get together. So, a summary of the electrical double layer. The first layer that we talk about beyond the edge of the particle is the Stern layer. The second layer, discovered by Gouy-Chapman, becomes the Gouy-Chapman layer. Zeta potential is defined by the edge of that solvent bubble, where that shear plane is. And finally, high zeta potentials will give very stable colloids that won't settle out. low zeta potential will encourage particles to be mutually attractive. So if you want something like milk, you want that to be stable and not settle, so you want all those particles of milk to have very high zeta potentials, the fat molecules. If you think about wanting a wet strength agent like MF and UF resin to be attracted onto a fibre, you want mutual attraction, and therefore you want low zeta potential. So I hope all that makes sense to you. You may feel it useful to go through that again. Thank you for listening, and please feel free to follow us on any of this social media.